In this video, we're going to take a look at function operations, and we're going to pay special attention to the function operation of function composition. So the first types of operations that we'll do with functions are our standard mathematical operations of adding, subtracting, multiplying, and dividing. Whenever we have two or more functions, we can do those standard mathematical operations on those functions. And the way we do it, when we're adding, subtracting, multiplying, or dividing functions, the way we do it is that we do the operation to the expressions that the functions are equal to. In other words, we do those operations to the expressions giving the outputs of the function. Now, notationally, when we add, subtract, multiply, and divide, we just use the standard mathematical notations. If we have two functions, one called f and one called g, the sum of those two functions is going to create another function. We write the sum of function f and g as f plus g of x, which is basically going to be the same thing as taking the output f of x and then adding the output g of x. When we subtract f minus g, we create a new function. So f minus g of x is our new function that we create by taking the output f of x minus the output g of x. When we multiply, well, we can use any symbol for multiplication that we want. F times g can just be written as f right next to g, or f dot g, or f, the cross multiplication symbol, and then g. But it just means take your output f of x and then multiply your output g of x. The same thing is true with division. Usually when we see division, we write it as f, then line g, as in a fraction, f in the numerator and g in the denominator. So f divided by g of x. You could also use the standard division symbol. And it's basically just taking the output of f of x and dividing by the output of g of x. This is obviously defined when the denominator is not 0. And these other ones are also defined on the domains of f and g. So if f and g are both defined over the entirety of the real numbers, then the sum, the subtraction, the multiplication will also be defined on that domain. If there are some restrictions on the domain of f, then there'll be some restrictions on the domain of f plus g. If there are restrictions on g, then there'll be restrictions on the domain of f plus g. So the sum, when you add the two functions, when you subtract the two functions, when you multiply the two functions, the restrictions on the domain line up with the actual original functions. When you divide the two functions, the restrictions on the domain still hold, but we have this added restriction that g of x cannot be 0. Let's do an example. Let's take f of x as the function you get when we take 3 times x minus 4 as the output, and g of x as the function whose output is x squared minus 1. And we'll compute f plus g of x, f minus g of x, f times g of x, and f divided by g of x. Each one of these is going to create a new function whose variable or whose input is x. We'll do these one at a time. Let's do f plus g of x. Basically, that's going to take f of x plus g of x. So we take the output 3x minus 4, and then we add the output of x squared minus 1. You can do the operations and combine like terms if you want. I'll combine like terms. X squared is the term of highest degree. Then 3x is next. Minus 4 and minus 1 would combine to give me minus 5. So f plus g of x is a new function whose output is x squared plus 3x minus 5. And we can do a similar thing for every single operation. Let's subtract. Let's take f minus g of x. Be careful when you subtract because the f here is 3x minus 4, has two terms in it. The g of x also has two terms. That is, the output of g of x has two terms. When you subtract, you have to distribute the negative sign. And in this case, the new function that you get out is negative x squared plus 3x, and then you're going to do a minus 3. Be careful that you do a minus 4 and then a minus a negative 1. That's going to add 1. So negative 4 plus 1 gives you the minus 3. Multiplication works exactly the same as you think it would. We take 3x minus 4 multiplied times x squared minus 1. And you just do standard polynomial multiplication. So each term in the first expression multiplies times each term in the second expression. You would get 3x to the third minus 3x minus 4x squared plus 4. So the new function that I get, f times g of x, I'll put it in descending order, would be 3x to the third minus 4x squared minus 3x plus 4. F divided by g of x, I take the expression for my output for f, which is 3x minus 4. That would be placed in the numerator. My expression for the output of g, which is x squared minus 1, that would be placed in the denominator. And that would just be my new function. There's nothing that's going to simplify that any more than it already is. So that's about as simplified as I can make it. By the way, notice that in this one, while the original functions had domains that were all real numbers, f divided by g has a domain that's all real numbers except for x equals 1 and x equals negative 1. So we can't plug in a 1, we can't plug in a negative 1 because that would make our denominator of this fraction be 0. That's not something to focus on right now, but that is just an observation that can't plug in 1, can't plug in negative 1 into the denominator because then you'd be dividing by 0. So this is pretty straightforward. Anytime we have two functions, if we want to add them, if we want to subtract them, if we want to multiply them, if we want to divide them, then we just do that operation to their outputs. Now that we've done that, we can say, well, this is a new function. F plus g gives me a new function. So what if I plug in 3 into that function? Or f minus g of 3, or f times g of 3, or f divided by g of 3. There are a couple of ways we can actually do this. Since we've already calculated f plus g of x, and f minus g of x, and f times g of x, and f divided by g of x, we'll use that work first, and then I'll show you another way as well. We're using the same f and g as the previous example, and in the previous example, I just found out that f plus g of x is x squared plus 3x minus 5. Therefore, f plus g of 3, actually, let's get rid of it up there. Let's put it below. F plus g of 3 is going to be 3 squared plus 3 times 3 minus 5. And then I simplify that. That's 9 plus 9 minus 5, which is 13. And that's one way to do it. We can do the exact same thing for f minus g of 3. Just go back up to our previous work. We found that f minus g of x is negative x squared plus 3x minus 3. So all I have to do is use that expression, negative 3 squared plus 3 times 3 minus 3. That's a lot of 3's around. That's negative 9 plus 9 minus 3. That gives you out a negative 3. So when you plug in 3, you get an output of negative 3. Same thing with f times g of 3. Our previous work showed that f times g of x is equal to 3x to the third minus 4x squared minus 3x plus 4. So all I would have to do is take that expression and plug in 3. We get 3 times 3 to the third power minus 4 times 3 to the second power minus 3 times 3 plus 4. That one I'm going to plug into my calculator. That's a lot of work. So when I plug that into my calculator, I got a 40. A lot of stuff to do by hand if we had to do it by hand. So f times g of 3 is equal to 40. And then the same thing when we divide. When we divide, I already did the division in general. So now let's do the specific division of f divided by g of 3. In the numerator, you take 3 times 3 minus 4. In the denominator, you take 3 squared minus 1. And so you'd get 9 minus 4, which is a 5, divided by 9 minus 1, which is an 8. So you end up with 5 over 8. as the answer of what happens when you plug in 3 into the function f divided by g. Now, in each of these, I use the previous work. You could have also done this another way. And the other way you could have done this is just plug in 3 into the original function f and plug in 3 into the original function g, and then added up the outputs. Remember, that's all you're doing here is f plus g is just adding the outputs up. So what I could have done to calculate f plus g of 3 is I could have plugged 3 into f and then plugged 3 into g and then added those two values up. Remember, we're using this same f and g we had before. F of x was 3x minus 4. G of x was x squared minus 1. Let me actually put that up here just so we can have that in our heads. So if I plug in 3 into f of x, I end up with a 5. If I plug in 3 into g of x, I end up with an 8. 5 plus 8 is 13. The same thing with all these other ones. When you subtract, we could have said f minus g of 3 is actually just f of 3 minus g of 3, which we've already established is 5 and 8. So 5 minus 8 gives me out a negative 3. Same thing with multiplication. I won't write down every step, but in this case, we could have said, oh yeah, f, I guess I will write down every step, f times g of 3 is actually f of 3 multiplied times g of 3, which is 5 multiplied times 8. We already knew those two, which gives you a 40. And then it's pretty easy to see that we could have done the same thing with the division operation too. F over g of 3 is like taking f of 3 divided by g of 3, which obviously is 5 over 8 as well. So if you don't want to do all of the operations, if I'm just wanting to, let me rephrase that. If you don't want to do all the operations in general, if you don't want to, for instance, take f times g of x and then multiply that all out, then instead of going through that process to find f times g of 3, you can just take f of 3 times g of 3. And sometimes that's easier. Either way, as we see, we're going to get the same answer. Let's take a look at example 2a. We have a cubic polynomial for f and a quadratic polynomial for my output of g. And let's compute the following. When I add, I'll probably combine like terms. When I subtract, I'll combine like terms. If I multiply, that's going to be a big multiplication process. So I think I'm just going to not simplify when I do the multiplication. I think when I divide, I won't simplify either. So If you want, try this on your own. Try computing f plus g of x, f minus g of x, f times g of x, f divided by g of x. And then after we do that, what we'll do is we'll plug in -1 in for those x values. So we'll do this in general with a general x value, and then we'll do it with a specific x value of -1. Again, push pause on the video if you'd like to try that on your own. In a couple of seconds, I will do it. Okay, so I'm going to do this and I'm going to kind of, well, I'll not do a lot of steps, but I'll show most of the steps. So f plus g of x, we do x to the third minus 2x squared minus 4x plus 7. And then we'd add, hit the wrong button there, x squared plus 5x plus 9. I'm going to combine like terms when I do this. So f plus g of x is equal to, I'm getting x to the third minus 1x squared. Look bad on my typing today. Minus 1x squared plus 1x plus 16. You can leave the coefficients of 1 off if you'd like and just put it there. In a similar way, when we subtract, all that's going to happen is I'm going to take that f of x expression and subtract g of x, the expression for the output anyways. And I can combine these as well. We get x to the third. I get a minus 2x squared and then a minus x squared, so that becomes minus 3x squared. Minus 4x and then minus 5x becomes minus 9x. 7 minus 9 becomes a minus 2. So that's the expression I get for f minus g of x. Again, notice when I add two functions, I get a new function. When I subtract these two functions, I get a new function. When I multiply these two functions, I'm going to get a new function as well. In this case, I don't think I'll do the expansion here just because that'll take more time than necessary. But what I will do is I'll write this down as x to the third minus 2x squared minus 4x plus 7 multiplied times x squared plus 5x plus 9. Make sure you have parentheses around that. And if you were to expand this, you'd have to multiply x to the third times these three terms, and then minus 2x squared times those three terms, minus 4x times those three terms, plus 7 times those three terms. Be a long thing, but very much doable. F divided by g of x, I'm going to take my expression for f, which is x to the third minus 2x squared minus 4x plus 7, and divide it by x squared plus 5x plus 9. By the way, I do want you to be aware, f divided by g of x is obviously not the same thing as g divided by f of x. So you'd have to use the reciprocal. Same thing with subtracting. It's very important that the f comes first minus the g. If I had g minus f, then I'd put the g first and the f next. So there we go. That's the whole thing. Now we're given these two functions, and we're also asked to plug in -1 into f plus g, plug in -1 into f minus g, plug in -1 into f over g. I think what I'm going to do, instead of plugging in -1 into this, and then into this, and then into this, and then into this, I'm going to start by plugging in -1 into f, and then plugging -1 into g, and finding my output using those two values. If you plug in -1 into f, we get -1 cubed minus 2 times -1 squared minus 4 times -1 plus 7. That becomes an 8. When I plug in -1 into g, I get -1 squared plus 5 times -1 plus 9. And that is a 5. By the way, obviously you don't always get 8 and 5. And I think this is pretty easy to do. F of -1 is 8, g of -1 is 5, and therefore f plus g of -1 is going to be 8 plus 5, which is 13. F minus g of -1, well, f of -1 was 8. G of -1 was 5, so that's going to be 8 minus 5, which is a positive 3. F times g of -1, again, f of -1 is going to be the number 8. G of -1 is the number 5. F times g of -1 is 40. Again, you're not always going to have 8s and 5s every time as your outputs, but this principle should make sense. F of -1, 8. G of -1 is 5. 8 over 5 is your answer. If you want to rewrite that as a decimal, that is a decimal is 1.6. Or if you want to write it as a mixed number, it's 1 3/5. So there you go. Once you find f of -1 and g of -1, then things work out nicely. Now, this shows you that you don't actually need the original expressions for f and g. As long as I know where f sends a number and where g sends the number, then I can figure out where f plus g sends that number, and where f minus g sends the number, and where f times g sends the number. So imagine that I am not given my f and g explicitly, but I know that f sends 5 to the output of -3. And when we put in an input of 5 into G, we get the output of 12. So the input of 5 into F is the output -3. The input of 5 into G gives the output of 12. Could we find the sum of the two functions where that sends 5? Could we find where 5 is sent when I take the difference, f minus g, or the product, or the division? If you want to push pause on the video, you can do this on your own. In a couple of seconds, I will do it. So f plus g of 5 is just f of 5 plus g of 5. I'll skip writing that step and just say, well, f of 5 was -3. G of 5 was 12. So f plus g of 5, that function should have output of 9. The function f minus g, when I plug in 5, should have output of -3 minus 12. And so the output should be -15. F times g of 5 should have output f of 5 times g of 5, which is -3 multiplied times 12. That's a -36. And f divided by g of 5 should be the fraction f of 5, -3, divided by g of 5, which is 12. Now, if you wanted to simplify that fraction simplifies to -1/4. If you wanted to write that as a decimal, that would be the decimal -0.25. So like both the last example and this example show, as long as I know where f and g send a certain value, I can figure out where the sum sends the value, where the f minus g sends the value, where f times g sends the value, and where f divided by g sends that value. Now, things can get more complex if you want. I've set up a couple of extra problems here that are a little bit more involved. You can see here we just have g over f of 2. We know at what f of 2 is. We know what g of 2 is. We have, in this case, 4 times f minus 8 times g of 2. And then in this third instance, we have f times g minus 3 times f of 2. You could do this in general as well. If I knew the expressions, I could do any sort of combination of adding, subtracting, multiplying, dividing. And then as you see here, we can also multiply by scalars. So I'm going to go ahead and do that in the same way we did earlier. G divided by F. In this case, we do 11 divided by 6. If you want to rewrite that, that's 1 and 5 over 6. Or if you wanted to use a decimal, you'd have to round a decimal or write that repeating. It's 1.83333 with the 3 repeating. Now for f minus 8g of 2 is exactly what it sounds like. We're going to take 4 times f of 2 minus 8 times g of 2 and compute that. Again, if we had an x in here, we do the same thing for x. In other words, 4, that constant number, is just like a constant function where you get f of x is equal to 4. Not this f of x, but a function having constant output value of 4. So 4 times f of 2 is going to be 4 times 6 minus 8 times g of 2. That's minus 8 times 11. 4 times 6 minus 8 times 11 gives an output of negative 64. And then, as you can see, we can have any combination that we want. F times G minus 3 times F, it's going to work the same way. F of 2 multiplied times G of 2 minus 3 times F of 2. So that's going to be 6 times 11 minus 3 times 6. So 6 times 11 minus 3 times 6 becomes a 48. And that's the final value there. This shows we can have lots of different combinations of these operations of adding, subtracting, multiplying, and dividing. And we do the natural thing. So those are our basic operations on functions: adding, subtracting, multiplying, dividing. And then we saw that we can also multiply by a scalar if we just replace the like the f with a number or the g with a number. We can do scalar multiplication as well. So each of these operations gives me a new function. When I add the two functions together, I create a new function. When I subtract the two functions, I create a new function. When I multiply the two functions, I create a new function. When I divide two functions, I create a new function. If I did any of those other operations or combinations of these operations, I'd create a new function. There's one more operation that we're going to look at. That new operation is the operation of function composition. If I compose or composing G of F, sometimes we say compose G with F or composing F of G, composing F of G, compose F with G. It means we plug the output of G in as the new input of F. Now, because this isn't a standard operation, like it's not just multiplication, it gets a new symbol. And the new symbol we use for function composition is a circle. So F of G, composing F of G, means we plug in the G output as the input for F. It's kind of like we do a couple of steps. We start with an input of X, and then we hit that with our function G. Our output of G becomes G of X. And that g of x becomes the new input for my function f. So it's kind of like doing two function operations, one inside of the other. This is composing f of g, or compose f with g. Again, order here is going to be important. The one on the right-hand side is going to be the inside function. The one on the left-hand side is going to be the outside function. Let's do an example. Here we have two functions. In fact, these are our original two functions we started with. F of x is equal to 3x minus 4, and g of x is equal to x squared minus 1. Let's compute f of g of x and compute g of f of x. I'll start with f of g of x. So what I have to do is realize that the f here is on the left, so that's the outside function. The inside function is the g of x. So basically what that means is I'm going to take the expression of g of x, which happens to be x squared minus 1, and that is going to be the input of the function f. So everywhere I see an x in my original function, I replace it with x squared minus 1. So I take 3 times the quantity x squared minus 1 and then subtract 4. So my original f had 3x minus 4, and I've just replaced this x with x squared minus 1 because that is the output of g. So I took the input g of x. I know that is x squared minus 1. That becomes the new input for my function f. So I replace every x I see with an x squared minus 1. And then if you want to, obviously you can rewrite that, combine that, simplify that, whatever you want to do. That would give you 3x squared minus 3 minus 4, which is 3x squared minus 7 when you combine like terms. So the composition of f with g becomes 3x squared minus 7. Notice that function composition also gives you a new function. Just like function addition gave us a new function, subtraction gave us a new function, multiplication gave us a new function, composition is also giving us a new function. If we do this in the reverse order, if I compose g with f, that is, if g is on the left-hand side, then f of x is going to be the input for my function g. F of x is 3x minus 4. So I'm going to replace the x in the expression x squared minus 1 with the quantity 3x minus 4. So I'm plugging in 3x minus 4 into my function g. That means replace every x I see with 3x minus 4. So we're going to get the quantity 3x minus 4, quantity squared, minus 1. Again, if you want to do a simplification of that, you can. You'll get 9x squared minus 12x minus another 12x, so minus 24x, and then plus 16 minus 1. I'll rewrite that as plus 15. If you want to simplify, that's what you'd get. You don't have to. You can leave it as 3x minus 4 in parentheses, quantity squared, minus 1 if you'd like. So that's the idea of function composition. We replace the input of f with the expression g of x. Or if you do it in the reverse, we replace the input of g with the expression f of x. Let's check out what would happen if we plugged in the number 5. We'll plug in f of g of 5 and then g of f of 5. Since we're talking about using the same f and g, one way I could do this is I could compute the composition of f of g of x. We know now that that's 3x squared minus 7. So I could just plug in 5 into 3x squared minus 7. I'd get 3 times 5 squared minus 7, which would be 3 times 25 minus 7, or 68. That's 75 minus 7, 68. So we could do that if we'd like. And the same thing is true if we did function composition the other way. If we did function composition g of f of 5, all we could, since I already calculated g of f of x, I could just replace every x with the number 5. So 9 times 5 squared minus 24 times 5 plus 15. And then I'd plug that into my calculator. And I'm doing that as I speak. I got 120 when I plug that into my calculator. So that's like the one way. Another way I could have done this is I could have found f of g of 5. Let's start here. By saying, what is g of 5? And then plugging that in for f. So g of 5 is what we get when we plug in 5 into g. 5 squared minus 1 would be 24. So that would be f of 24 because g of 5 is 24. And then I could take 24 and then plug it into my function f. 3 times 24 minus 4 becomes 68. Notice that we got the same thing. Now, if I did the reverse way, I shouldn't have erased that one. I tried to do that on purpose. If I did it the reverse way, I would first plug in 5 into my function f. If I plugged in 5 into f, I'd get 3 times 5 minus 4. That's 15 minus 4, which is 11. So f of 5 gives me an 11. And therefore, I'd put 11 in as the input of G. 11 squared minus 1 is 121 minus 1, which is 120. Notice again, I'm getting the same result either way. 120 and 120, but I'm just getting them in a slightly different method. So just like before, if we know all of the inputs and relevant outputs, then we can trace that out. We can figure out what that is, what the output's going to be. Now, I hope that we all noticed that when we did function composition was not commutative in our previous example. So in general, function composition is not commutative. When we did f of g of 5, we got 68. When we did g of f of 5, we got 120. And we saw we also got different expressions when we did f of g of x as when we did g of f of x. So function composition is not commutative. I have to really pay attention to which function is on the left and which function is on the right when I do function composition. Let's try another example. Here we have example 6a. We have a function which is the absolute value of x plus 3. The x plus 3 is inside the absolute value symbols. And g of x is equal to x minus 9. So f of x is the absolute value of the quantity x plus 3. G of x is x minus 9. And we're going to be asked to do the function composition f of g of x and also the function composition g of f of x. After you do that, I want you to plug in -7 into the f of g of x and then the g of f of x. And you can use either method to find this. You can plug in -7 into your expression you get, or you could plug in -7 into the first function and then plug the output into the second function. So either way. If you want, push pause on the video, try to do that. In a couple of seconds, I'll show you how that's done. In the first one, composing f of g of x, what I would do is take f and then input the g of x inside of there. So what that means is I take f and I input that expression, which is x minus 9, for the new input of f. This means everywhere I see an x, I replace it with x minus 9. And that gives me the absolute value of quantity x minus 9 plus 3, which I can rewrite as the absolute value of x minus 6. So the composition of f of g of x gives me absolute value of the quantity x minus 6. G of f of x On the other hand, I would take the g and I'm going to input the output of f of x. So for my input for g, I'm going to plug in absolute value of x plus 3. So this becomes the absolute value of x plus 3 and then minus 9 on the outside of the absolute value. Hopefully everybody knows what absolute value does. If you put in absolute value of a negative number, you get back the positive of that number. If you input a positive number, you get out the positive number itself. So if we plugged in a -7 into f of g, that would be the absolute value of -7 minus 6, which I have to compute what's inside first. So that's the absolute value of -13. Again, absolute value of a negative number gives me a positive number. So absolute value of -13 gives me a positive 13. On the other hand, if I did g of f of -7, I take absolute value of -7 plus 3. That -7 plus 3 is inside my absolute value. And then after I took the absolute value of that, I would subtract 9. That's going to give me absolute value of -4 minus 9. And that's going to give me a positive 4 minus 9. So 4 minus 9 becomes a -5. So f of g of -7 gives a positive 13. G of f of -7 gives me a -5. And once again, like I've said before, you could have also done the tracing steps as well. I don't have to, if I plug in a -7, I don't have to get this simplified version. I can ask myself, well, when I plug in -7 into G, what do I get? Well, if I plug in -7 into G, I get -16. -7 minus 9 becomes -16. And then when I plug in -16 into x plus 3, I get -16 plus 3, and then that goes in absolute values. That's the absolute value of -13, which gives me 13. And then we can do that in reverse as well. If I wanted to plug in -7 into the composition, I could do composition of g of f of -7, means plug in -7 into the f. When I plug -7 into there, I get -7 plus 3 inside of the absolute value. So I get -4 inside the absolute value, which gives me a positive 4. So plugging in a -7 into the f, the output of f becomes 4. And so I plug that 4 into G. And then 4 minus 9 becomes -5. Again, either way, we're getting the same answer. This shows that we can do that composition without knowing the specific expressions for our functions. As long as we know proper inputs and outputs, then we can actually kind of trace through this diagram and say, where is a number sent by our function g? What output do I get? And then what does that new output, where is that sent by f? Now you have to be careful, obviously. You have to always do this in order. So if I do f of g, I'm doing it in this order. If I did g of f, I'd be doing it in the reverse order. So as long as we know where g sends certain values and where f sends certain values, then we can do compositions. Let's do this example. Now, there's a lot of different compositions that we are asked to do. So there's a lot of input values that it's giving us, both for my function f and for my function g. So it's giving me lots and lots of input values and lots of output values so that I can kind of trace through what's going on here. So let's go ahead and do this example. The first composition that we'll do is f of g of 4. So that's going to require me to start by inputting 4 into the function g. So I go and look up my function g. Now these are not the same f and g as I had before. These are just random f's and g's. So g, it says, sends 4 to 9. So the input of 4 into g gives me an output of 9. That output is going to be my new input for my function f. So we're going to say, where does f send the input of 9? Well, f sends the input of 9 to 1. That means f of g of 4 is equal to 1. We can do the same thing for 10 as well. We say f of g of 10, start out by trying to figure out where g sends the number 10. G sends the number 10 to 7. So the input of 10 into g gives the output of 7. That 7 is going to be my new input for my function f. If I input a 7 into my function f, I get an output of 4. So f of g of 10 is equal to 4. So this new function, which is made up as the composition of f of g, sends the number 10 to the number 4. And it sent the number 4 to the number 1. Now let's compose in the reverse order. Let's do g of f of 4. G of f of 4, I first start out asking, where does my function f send the number 4? F sends the number 4 to the output of 2. So that output of 2 becomes my new input for my function g. G sends the input of 2 to an output of 4. Therefore, g of f of 4 is equal to 4. So g of f sends 4 to itself. Let's do g of f of 7. G of f of 7. G of f of 7. We ask, where does f of 7 get sent to? F of 7 gets sent to the number 4. Therefore, we're going to calculate g of 4. And g of 4 is equal to 9. So g of f of 7 is equal to 9. Now let's look at this last one. This last one says g of f of 9. Well, f of 9 is 1. So we say the output of f becomes the input of g. Let me put that on the page. So therefore, we're looking for g of 1. Now, here's the deal. Right now, I don't know where 1 is sent to by g. I know g sends 4 to 9, sends 2 to 4, sends 10 to 7, but it doesn't tell me where 1 is sent to. So basically, g of 1 is not defined by what I have up here. G of 1 is undefined, or unknown is another way you could write that. Again, this is happening because I don't know where g sends 1. If I had an actual expression for g and the domain was all real numbers, then I'd know where g of 1 is sent. But in this case, the domain I have for g is just the 3 numbers 4, 2, and 10. So since 1 is not in the known domain of g, I don't know where it's at and where that g of 1 is sent. Hopefully that makes sense. In general, I probably wouldn't give you one which is undefined on a homework or on a test question without giving you that option. That example showed that I can do function composition and I can know where f of g sends a value. I can know where g of f sends a value as long as I know the correct inputs and outputs for specific values. If I don't know those inputs and outputs, then I can get stuck. But if I know the specific inputs and outputs, then we're good to go figuring out function composition. You can even do this graphically as well. We've dealt with graphs of functions. So let's say this left-hand side graph is what we'll call f of x. So that's the graph of f of x. And the g of x is the graph on the right-hand side. could we do function composition? Could we calculate g of f of 2 and g of f of 6 and f of g of 0 using these two graphs of the functions? Well, the short answer is, of course we can, or else we wouldn't be asking. We just have to figure out, remember, x values are our inputs, y values are our outputs. So we can get the corresponding inputs and outputs for G and for F by looking at points on those graphs. Let's go ahead and do that. So start out by doing f of g of 2. So we're going to take f of g of 2. That means I first need to figure out what g of 2 is. Now, g of 2 can be found by the right-hand side graph, the one in the red. Notice that when you put in an x of 2, you get a y value of 1. So what we're at here is the point 2, 1. That means when I input a 2 into G, I get the output of 1. So that means in my next step, I calculate f of 1. Well, what is f of 1? F is represented by the left-hand graph here. When you input the x value of 1, the corresponding y value looks to be negative 1.5. That might be hard to see, so you might have to like zoom in a little bit on that graph, but it looks to be about negative 1.5. And in fact, it is. So the point 1 comma 1 point, negative 1.5 is on that graph of f. So that would be our first composition. F of g of 2 gives out a value of negative 1.5. What if we did g of f of 2? Well, if we did g of f of 2, the first thing we need to do is figure out what f of 2 does. Once again, we turn to the graph of f, which is here on the left. When we input an x value of 2, you get a y value of negative 1. So g of f of 2 becomes g of negative 1. And then g of negative 1. Well, when I put in a negative 1 into my function g, I get out a negative 2. We're at that point there. And so g of negative 1 becomes a negative 2. So g of f of positive 2 gives out a value of negative 2. Lastly, g of f of 1, g of f of 1. Plug in 1 into f. Remember, the f is on the left-hand side. Let's clear those other points. When I plug in 1 into my function f, I get a negative 1.5 as my output. And then if I get a negative 1.5 as my output, that becomes the input for g. And it looks like that point is a negative 0.75. If you look at where negative 1.5 takes me to negative 0.75. Again, you may need to zoom in on these to see accurately. But what I'm saying is if you input a 1 into F, you're at the point 1, negative 1.5. And if you plug in a negative 1.5 into G, you get right here, which is negative 0.75. I can see that because each unit is broken up into 4 kind of tick marks. So there we go. Let me write that down. When we plug in 1 into F, we get a negative 1.5. When we plug in negative 1.5 into G, it looks like I get a negative 0.75. If I gave you questions like this, they should be able to be seen as long as you zoom in on the picture enough. Let's do another example of computing f of g of 2, g of f of 2, and g of f of 1, but we'll use different f and a different g. In this case, again, f is going to be the left-hand side graph, g is going to be the right-hand side graph. Left here, the left-hand graph is the one in blue, right-hand graph is the one in red. Try these 3 on your own if you'd like. In a few seconds, I will show you how each is done. I'll do those now. So here we go. F of g of 2. That means I need to plug 2 into g. That's the graph on the right. So you can see that this graph on the right goes through the point 2, comma 2. So if you input 2, your output for g should also be 2. So input of 2 gives an output of 2. So therefore, I'm calculating f of 2. F represents the graph on the left, and f of 2, it looks like when you plug in 2, you get an output of 4 because your graph goes through the point 2, comma 4. So f of 2 is equal to 4, and therefore f of g of 2 is equal to 4. Now let's go the reverse way. G of f of 2. Well, we just got done saying f of 2 is equal to 4 because our graph of f, the one on the left here in blue, goes through the point 2, 4. Therefore, the input of 2 into f gives an output of 4. That output of 4 becomes our new input of g. And if we trace it out, well, our input of 4 into g gives an output of 0 because our graph of g goes through the point 4, 0. Lastly, we take g of f of 1. Again, f is the graph on the left. We can see that when you plug in a 1, you should get a 3 because the graph goes through the point 1, 3. That means g of f of 1 is the same thing as g of 3. And then let's figure out what that does. Well, when I plug in a 3, into the graph on the right, I'm at the point 3, 1. Therefore, the input of 3 gives an output of 1. So g of 3 is equal to 1. So this is how we can use graphs of functions, of two different functions, to do function composition. And obviously, if we have screenshots of these graphs, I don't necessarily know what g of 10 is because that's way off, the side of the screenshot. I don't know what f of 10 is because that's off of the realm of the screenshot. But you can imagine with the right windows, you could find g of 10 and f of 10 and any other number that you wanted. So that shows you how to do function composition by just knowing what points the functions go through or what points the graphs of the functions go through. And that's the idea of function composition. This function composition, x goes into one function and then the input of that, the output of the first function becomes the input of the second function. We saw how to do that with algebraic expressions. We saw how to do that with numerical values and algebraic expressions. We saw how to do that by using numerical values alone. And then lastly, we saw how to do that using functions and their graphs. So function composition is exactly that. That is a really important function operation in this section. Obviously, you shouldn't forget the other function operations of function addition, subtraction, multiplication, and division as well. So these ones. Again, one thing I do want to mention before we end this video is be careful of this symbol here, this dot multiplication versus the function composition operator of an open circle in between there. Some people get confused because they'll put their multiplication symbol in and they'll draw it as a dot. Other times, if they're sloppy about drawing it, they'll draw it as an open circle. And remember, open circle is our function composition. A dot means multiplication. And that's why when you saw me do the examples that I did, I favored this multiplication, just doing f and g next to each other, rather than using a dot there, because then you don't get confused with multiplication and function composition. So be careful of that. Function composition has that open circle, and multiplication sometimes can be a dot or just no operation symbol in between F and G. But there you go. So that composition operator. And don't be thrown off if it says F of G as well. A lot of people just start with this right-hand notation on the composition as well. And that kind of avoids any problems they have with drawing the composition operator symbol. So a lot of people just write this. So anyways, that's operations on functions, and that is the end of this video.